Chemistry 1, we learned that water is called the universal solvent. What do you guys remember from the universal solvent last year?
Oh, yes! Yes! No, I found
it's incredibly polar.
In second hour, I found those videos on my phone, and I had to watch them all.
Evan, you just want to be on.
It was amazing. Oh, she's recording. Yes.
Oh my god. We are 2 weeks away from the midterm, as of today. Just FYI, 2 weeks away from the midterm.
Wait, what?
So anyway, from those videos last year, we learned that water is extremely polar. What else does anybody remember about the universal solvent? It can dissolve a lot of things, and when those things are dissolved, then they have electrolytes. Yes.
Hydration!
Waters of hydration, yes, happen when you have crystals that have water involved. Oh, right.
So what do I write?
Great. Don't write anything, just think about it.
Oh, well, I wrote.
Good for you. So, like Aiden said, water is a polar molecule, which makes it able to dissolve most compounds. Its polarity allows it to dissolve both ionic and polar covalent compounds. So this picture shows the ionic form. And what is that interaction called between the ions in the waters? Which type of intermolecular force? Yeah, but what else?
Hydrogen bond.
Nope. It contains ions.
Ionic.
What did you say?
Ion dipole.
Ion dipole. Yes, ion dipole.
I was going to get there one day.
Oh my goodness.
I had it in my
That is on the test. It's going to be on whatever day that is, just FYI. I want to show you water interacting with ethanol. Ethanol is similar to the isopropyl alcohol that we use in our lab. Isopropyl alcohol has an extra prop, stands for 3 carbons. F stands for 2 carbons. But so the part of ethanol that is polar is just that OH group right there. So the only interactions that water can have with making polar bonds or using hydrogen bonding is with this spot right here. Only with this part. So there are a lot of other factors that depend on how you dissolve things, but that's to show one structural way that an ionic compound is different than a polar covalent bond, a polar covalent compound dissolving in water. There's less interactions with polar covalent. Nonpolar substances are when they don't dissolve in water, usually because they're nonpolar. For example, pure water doesn't dissolve animal fat. This is what a fat molecule looks like. The reds are oxygens, the black ones are carbons, and the white ones are hydrogens. And it's like have you ever heard of triglyceride? Yes, triglyceride. The reason why it's called that is because of these 3 branches.
It looks like a nerd.
Yeah, it does, doesn't it? So maybe after the AP exam, maybe we can eat some nerd ribs and learn more about fat molecules. Fat molecules are nonpolar and don't interact effectively with the polar water. So that's why if you've ever gotten like bacon grease or cooking grease, and then you let it cool, and then you see the grease sitting on the top, it's because they don't mix, because they're nonpolar versus polar water. We encounter dissolving solutes and liquids every day in life. This is a picture of gasoline sitting on top of water. That's why that's there. So we mainly need to know that like substances dissolve like. So polar solvents dissolve polar compounds and ionic compounds, and nonpolar solvents dissolve nonpolar compounds. In order to form a liquid solution, we separate the solute into its individual components, overcome intermolecular forces in the solvent to make room for the solute, and allow for the solute and solvent to interact together to form the solution. So this kind of shows that when it says you break the intermolecular forces, what it means is the molecules have to spread out, because if they're really close together, there's no room to intersperse the solute into it. So not only does the solute break apart and expand, so does the solvent. And then when they're both bigger and expanded, then there's space for the 2 of them to mix together. So there is energy associated with this because we have to break bonds, so that requires energy. The enthalpy of solution, or heat of solution, is the sum of the enthalpy values for each step involved for the formation of a solution. So the total enthalpy of solution is equal to each of the parts changes in enthalpy. The sign on the delta H may have a positive sign or negative sign. If it's positive, that means that energy is absorbed, and if it's negative, then it means the energy is released. Does anybody remember those words when it's absorbed energy and released energy from Chem 1?
Absorption, release.
Endothermic and exothermic are correct. Yes. So this is on page 515 in your textbook, if you wanted to look at it later. But picture A, shows, do you see how the heat of solution is lower than the other energy values? When it's lower, do you think that means that it's released energy? Do you think it's absorbed energy?
Release.
It's released. So A is a picture of an exothermic reaction because the energy is lower. And then for B, the energy of the solution is higher than the energy of the separated. So then that would be endo.
I don't think I ever fully understood those. Which ones? Like, which?
When it gets hot for you, it's exothermic because the system, which is not you are the surroundings. The surroundings are getting the heat, so it's exiting the system. So it's
Endothermic is when
exothermic.
the inside's getting.
Yes, so it feels cold to you. Yes. We'll talk about that at some point. I just don't know what that is yet. This year. Okay, so for example, dissolving sodium chloride. We have the solid sodium chloride takes 786 kilojoules per every mole to break it apart into its ions. And then for the delta H hydration, which is step 2 plus step 3, is the negative 783 kilojoules per mole. The hydration is the heat of hydration that combines the terms of delta H2 and delta H3. And this just helps us to represent the dispersion of a gaseous solute in water. It is a number that you could look up. So to find the delta H of the solution, the enthalpy of solution, we would take step 1, 786, minus the combined 2 and 3, which technically is plus, but it's a subtraction, so I guess I should show that to you. So the answer would be 3 kilojoules per mole. So it's a positive number, so do you think it's endo or exo? Endothermic, because it's positive. So that means that there's gaining of energy. It's a very small number, though. 3 kilojoules is really not that much compared to 786 kilojoules. So it's small, but it still shows, if it was 0, it would say that it required no energy extra whatsoever, or wouldn't have any other extra energy created, but it does have some. So it will create just a little bit, or need a little bit absorbed into it. There are other principles to consider. One of them is an increase in probability. Like, are you using salt from a salt shaker to dissolve, or are you taking like rock salt, which is really big chunks, to dissolve? So how the surface area is something to consider. That would help increase the probability. And processes that require large amounts of energy tend to not occur. So on page 517 in your textbook, there's another example that will help you with any homework problems. But we're not going to spend the time on it right now. Okay, so let's talk about how can we change solubility of things. For example, we can figure out, or we can compare fat soluble versus water soluble. So polar versus non-polar, non-polar versus polar. Very common things are vitamins, because we take vitamins, right? Does anybody ever know, like, has anybody ever taken like a vitamin C tablet or any set of vitamins before? So you might feel like they don't work because if it is water soluble, guess what? You are going to have that process through your body super fast, and guess where it's going to come and leave your body? Through your urine. Okay, so that's why, like, if you're taking vitamins, you have to take it every day, because even though it's 100% of your daily intake, your body is going to process it, and you're not going to actually absorb those vitamins very well. So I have vitamin A versus vitamin C. Okay, can you guess which one is the more polar of the two? Who says A? Who says C?
I put C.
C is the correct answer. Yes. So vitamin C is the polar versus the non-polar is vitamin A. Why did you guess that that was polar? Yeah, there's more OHs. So they do have them kind of highlighted, but the OH groups, they're called hydroxyl groups in organic chemistry. The more hydroxyl groups you have, the more polar it tends to be compared to having only one. That makes it a lot less polar. So the vitamin A is a fat soluble, and then soluble, and polar makes it water soluble. So our bodies will process those differently. Like one thing that they say to do when you get sick is to take lots of vitamin C, but like you can take lots and lots and lots of vitamin C because your body isn't absorbing it, even if you're taking like a supplement for that.
What if we take the whole bottle?
That wouldn't be good for you.
Really?
No. It's like that would be like overshock to your system, and it wouldn't be good.
I felt good.
Pressure does little to change the solubilities of solids or liquids, but it does have a large effect on the solubility of a gas. So, carbonated beverages are bottled at high pressures to ensure that the concentration of carbon dioxide to the liquid is there to create fizzing when you open the container. So, that's the whole point of like behind a pop can being sealed up. So they use what's called Henry's law to relate the concentration of the gas to the pressure of the gas. So C is the concentration. Usually C will be in molarity or moles per liter. Usually pressure will be in atmospheres because the K is the constant, and that'll be given to you most likely if you don't have to solve for K. But the unit for K would be, I think it's, oh gosh, where is it? It is moles per liter atmosphere. So if you forget what the pressure unit is, or you forget what the concentration is, the constant has it all in there for you. Okay? So Henry's law states that the amount of a gas dissolved in a solution is directly proportional to the pressure of the gas about the solution. So we're going to do example 19 as if we were working at a soft drink company having to bottle up our stuff. Okay? A certain soft drink is bottled so that a bottle at 25 degrees Celsius contains carbon dioxide gas at a pressure of 5 atmospheres over the liquid. Assuming that the partial pressure of carbon dioxide in the atmosphere is 4 times 10 to the negative 4 atmospheres, calculate the equilibrium concentrations of the CO2, the CO2 in the soda both before you open it and after the bottle is opened. The constant for CO2 in aqueous solution is this number right here at 25 degrees Celsius. Okay, so we're going to find two answers. We're going to find the pressure before, or sorry, the concentrations before we open the bottle and after we open the bottle. So we need two different answers. So we're going to see this difference in concentration. Remember, it's molarity, so it's how many moles of the gas are dissolved in a liter of the solution. So the unopened part, what pressure? We're given two pressures, 5.0 atmospheres and 4 times 10 to the negative 4. Which one is for the bottle before it's opened? The 5.0. Yep. The pressure of the carbon dioxide above the liquid means that it's contained, it's an enclosed container, and that is the 5.0 atmospheres. Okay, for both of these situations, we know that the K is 3.1 times 10 to the negative 2 moles per liter atmosphere. Okay, so we're going to use our C equals K times P to solve for the concentration. So we'll take our 3.1 times 10 to the negative 2 times 5.0. So the concentration is 0.16. Daniel, let's try that. . 0.16
155.
155, so two significant figures. I did okay. Awesome, thank you. Okay, so before you open up the bottle of the soda, or pop, whatever you want to call it, the concentration was 0.16 moles per liter, or 0.16 molar. So now let's compare that to when it's been opened. Okay, so now we know the partial pressure of carbon dioxide in the atmosphere. So when it is not a sealed container anymore, when it's opened up, the partial pressure is 4.0 times 10 to the negative fourth atmospheres. So we're going to use the same equation again, and we're going to use the same constant again, because it's still the same substance. So we'll take 3.1 times 10 to the negative 2 times 4 times 10 to the negative 4.
0.000124.
Okay, I put it in
Four
some.
zeros.
I put mine in scientific notation, so with negative 5. Would that be right?
Yes.
Okay. That's per liter. Okay, so after the bottle's been opened, the concentration is significantly smaller, right? So this is actually an example mathematically of why when you open up your soda bottle or your pop can and you let it sit for a while and the gas is able to escape, that your pop goes flat. Because eventually the gas will leave the liquid, and so that's why your drink tastes flat when it's done. There's no more fizz because the carbon dioxide leaves. So any questions about using that equation? Okay. Another factor that will affect your solubility is temperature. The dissolving of a solid occurs more rapidly at higher temperatures, but the amount of solid that can be dissolved may increase or decrease depending with temperature. So this picture, this graph is on page 520 in your textbook. So if you look at it, do you see how at temperature equals 0, the solubility has kind of set numbers except for sodium sulfate, or sulfate for some reason. Doesn't start. That must mean it's not soluble below that temperature. And then in general, most of the trends as you increase temperature increase. Sodium bromide doesn't really change there. And then these two kind of go down. So in general, it will dissolve better at a higher temperature, but sometimes there are cases when it doesn't. Predicting the solubility based on temperature is really difficult to do. The only way to determine this is by experimenting with that solid. So you won't really have much questions about that, like, is this going to tend to dissolve better or worse? You would just have to look at experimental data to decide that. The behavior of gases dissolving in water appears to be less complex than solids. The solubility of a gas in water will typically decrease with increasing temperature. Why do you think that is? If a gas dissolves less with a higher temperature, does anyone want to take a guess why that happens? Do gases move more or less at higher temperatures? More. So if it's at a higher temperature, the gas is going to be moving more, and so it's going to be harder to trap it in the solution. So that's why that makes sense. And this has very important environmental implications, like have you ever heard of greenhouse gases? And how if the Earth average temperature is rising, then that means that we're trapping less gases. And if we're trapping less gases, then those gases are being stuck up into the atmosphere, which then creates the greenhouse effect and all those kind of things. So, yes. So that is what some scientists are studying with our Earth, and it has to do with the solubility of the gas dissolving in the solution. When you have a solution, you will have vapor pressure above it, which we've talked about before. Liquid solutions can have physical properties significantly different from those of the pure solvent. So how a non-volatile solute affects the solvent is shown here, and I realized that I didn't include the picture in your notes. But so in A, which this is on what page? This is on page 521, if you want to make a note for yourself. In A, this is the beginning, where you have a beaker of water and a beaker of an aqueous solution in an enclosed container. Okay? What will happen is some of the water will escape, turn into a vapor, and then it will go back and get into the aqueous solution. So eventually, what do you think happens to the concentration of the solution? Do you think the concentration increases or the concentration decreases? The concentration decreases. Because if you're adding more water, it's just like you're diluting it. You're making it less concentrated. And then like all of the water can completely leave its original beaker, and it could either be vapor or it could be trapped in that aqueous solution. When you have solute particles, the solute particles trap the waters into that solution because of the ion-dipole interaction. So in general, the vapor pressure of the pure solvent is higher than the vapor pressure of an aqueous solution. And that's because the aqueous solution has those particles to trap it in, so it's less likely to turn into a vapor. It's more likely to turn into a vapor if it's just pure of the substance by itself. So, having it, like I just said, the non-volatile solute lowers the vapor pressure of the solvent, and it should be proportionately lower because the more solute you get, or the more solvent you get trapped in there, the less likely it'll be to happen. And it all has to do with the intermolecular forces. Okay. So, the next equation we have is called Raoult's law. I don't know if that's how you say it, but that's how I say it. So, that is the observed vapor pressure of solution, is key solution, is equal to the mole fraction of the solvent times the pure vapor pressure of the solvent. So this 0 stands for the pure, not the solution. It's like, so when you have a problem, you're going to have maybe sometimes two pressures given. And so you have to be careful, is it the solution's pressure, or is it the pure by itself, not in the solution pressure? Okay, so that 0 is there. Remember with mole fractions, if we want the mole fraction of the solvent, then we have to put the moles of the solvent over the total moles of the solution on the bottom. Okay, we have done that before. Note that for any solution of half solute and half solvent, the mole fraction is equal to 0.5, so the vapor pressure is half that of the pure solvent. You could do all the math and not remember that though, and that's okay. So, here we go. Calculate the expected vapor pressure at 25 degrees Celsius for a solution prepared by dissolving 158 grams of common table sugar, or sucrose, in 643.5 cubic centimeters of water. At 25 degrees Celsius, the density of water is 0.9971 grams per cubic centimeter, and the vapor pressure is 23.764. Okay, so when you're dissolving a solid into a liquid, it's really easy to see what's the solute and what's the solvent, right? So what's the solute here? The table sugar. Yep. So I think I have another slide, so I can write on the next slide. Move. Just go. No, I don't. Oh well. Okay. So I'll just have to delete, I guess. So we know the solute is the. Okay.
There it is.
There it is. I even have less room. Goodness. Here, I'll just turn this off. Discard it. And here, and here. Okay, so we know that the solute is the sugar. Okay, and we know that the solvent is then by default what? The water. Yep. Okay, so when we're solving for this equation, we need the mole fraction of water, because we said water is the solvent, and we need to multiply that by the pure vapor pressure of water. Okay, so in the problem, we are given 158 grams of sugar. We're given, so that's 158 grams. You don't have to write this down, but you can if you want to. And we're given, for the water, the solvent, we have 643.5 cubic centimeters of water. What do you think we need to do with those parts of the information? If we have to eventually plug into this equation, where do you think that will help us with this equation? What is this X thing called? What do you say? Yeah, mole fraction, right? So if it's a mole fraction, do we need moles of everything?
Yeah.
Yes. So we need to find the moles of sugar and we need to find the moles of the water. Okay? So the nice thing about this problem is that you are given the molar mass of the sugar, right? And we're going to divide by the molar mass. 342.3 grams. So I got my moles to be 0.4616. Ish. I didn't write down the whole number. Okay. And then we need to find moles of water. We are given cubic centimeters of water, and we are also given the density of water. Can we use the density to find the grams and then from the grams find the moles? Yes, that's what we have to do. So for the water, you could plug it into the density equation, but I like to do this. So this is how we're doing it on the notes. I take the volume times the density, because that's grams for every 1 cubic centimeter. And then you could pause here, but we're just going to keep going. So now, this canceling the centimeters cubed, now we can just divide by molar mass of water to find the moles of water. Anybody remember what that is? Yep, 18.02 or 18.1015, whichever one you would like to use is fine. So the moles of water I got to be 35.60. Yeah. 63? 62? Oh, okay. Did you do the 1.5? Or did you do the 0.02?
95.616.
Okay. Alright, so now we are not going to just plug in the moles of water to this equation because it's not moles of water, it's mole fraction of water. So mole fraction is moles part over moles total. Okay? So for the mole fraction, we have what we want, 35.62 over total. So we add them together. So 35.62 plus 0.4616. So I'm going to let you guys solve that because your numbers are a little different than mine. So the number I have written down is different. What did you get? Oh, I just want the whole answer. What?
Don't type it in all at once. That doesn't.
Yes, you need to add the two together on the bottom and then take top divided by bottom. Unless you wear a genius at the parentheses. It should be like 0.9 something. 9872. You might have divided bottom divided by top. It should be less than 1 because the bottom should be bigger than the top. Okay, so then now this will get plugged in here. What are we going to plug in for this one? Look up at the problem. Are we given a pressure anywhere? At the very end, it says the vapor pressure is 23.67. It's supposed to say, like, the density of water is listed there, so that is the vapor pressure of pure water. Okay? So that 23.76 is going to go right here. Alright? So to find the P solution, the pressure of the solution, we're going to take our 0.987 0.72 times 23.76.
Doesn't it have to be in 18?
As long, we're just going to report in torque. It'll be fine. That other equation had to be an 18. For this one, it doesn't have to be. So let's keep rounding to 4 significant figures. The answer is, hey, that's the same as mine. And then, so, good question. Since this is torr, our partial, or our pure pressure is torr, we're going to report our P solution as torr. And it will be fine. Okay?
Wow.
Yeah, don't worry. Number 22 is even bigger. I'm not going to take the time for 21. If you want help on that later, I can. The only difference with having an ionic, so this is an ionic option because it has sodium sulfate. When you have an ionic compound dissolves, it breaks apart into its ions. So its concentration, or the number of moles, just like how you're supposed to be doing, I think on 3.9 homework, or maybe it was 3.8 homework, when you find like the molarity of the ions, you multiply that by the number of ions present. When you are dealing with this problem and you solve for the moles of your solute, which is the sodium sulfate, you have to take it times the number of ions present, which in this case, there are 2 sodium ions and there's 1 sulfate ion. So that makes a total of 3 ions. So when you find the moles of your solute, then you would take it times 3 in order to get the correct answer. So if you would like to, in your own time, work through that, and I can work it through with you, I can do that. But that is just a hint for that, and you probably have a homework problem like that. I will leave it up here for a second. But otherwise, everything else is the same for that example of what we just did in 20. But it's because it is an ionic compound that breaks apart into its ions that you have to take that into account. Okay, we're moving on. This will be on the video. Like, we have 5 minutes left. So I gotta get through it. Seriously. Okay, so sometimes you don't have ideal solutions because, you know, we don't have ideal gases either. So when you have liquid-liquid solutions, so when you're combining 2 liquids together, the way that you tell what's the solute versus the solvent is the solute has less and the solvent has more. So if you had like 50 milliliters versus 100 milliliters, the smaller amount will be the solute and the larger amount will be the solvent. Okay, so we would add up the total for a liquid-liquid solution mixture where we take the partial pressure of each of the liquids together, which would relate into the mole fraction of that times its pure pressure plus the mole fraction of that times its pure pressure. Okay, so you have to pay attention. Now, mole fractions add up to 1, so if you know one of the mole fractions, you just subtract from 1 by the other mole fraction. Okay? A liquid-liquid solution obeys Rhodes' law, and we call it an ideal solution. It's like an ideal gas where it's never fully achieved, but sometimes closely approached to being ideal. And this table helps us with our interactive forces about like what it will be endothermic or exothermic. What are some examples of that and that kind of thing. But it's showing like how do the interactions react and how does that help us with our changes in enthalpy. Okay, so this is our last example. We are dealing with acetone and chloroform. So we have 5.81 grams of acetone and 11.9 grams of chloroform. Which one is going to be our solute? Which one has less? The chloroform or the acetone? The acetone. So our solute is going to be the acetone. I'm going to just put A for acetone. Okay? And our solvent would then be C for chloroform. Okay? So we are given that there's a total pressure of 260 torr. Is this ideal when you mix them together in these ratios? The vapor pressures of the pure forms are 45 and 293 torr respectively. Okay, so what we need to do, we have our P total is equal to the mole fraction of A for acetone times the pure pressure of acetone plus the mole fraction of C for chloroform times the pure pressure of chloroform. Okay? We're going to do the same thing that we just did, except for we have to do it twice because we have two different solutions, two different liquids adding together to make this solution. Okay? So for acetone, A for acetone, I know that I have 5.81 grams. So we are going to divide by molar mass. And we're given that the molar mass is 58.1 grams per mole. And when you divide that, it's going to be 0.1 moles of A for acetone. And we'll do the same thing for chloroform, C for chloroform, 11.9 grams of C. Divide by the molar mass of chloroform, which they give you is 119.4. So again, we divide that, it's about 0.1. Okay, we are given the pure pressures. We're given, so it says 345 and 293 at the end of the problem. Okay, those are, it's acetone first and chloroform second. That's what respectively means. It goes in the same order. So the 345 will go in for the P0 of A, and then the 293 will go for the P0 of C. What we need to find are the mole fractions of both of them. So which would you like to solve for the mole fraction of first, A or C? A. Okay. So for the mole fraction of A, I take the mole of A, which is 0.1, over totals, so 0.1 plus 0.1. So that turns into 0.1 over 0.2. What is that? A half. Yep. So if I know that the mole fraction of A is 0.5, the mole fraction of C is 1 minus mole fraction of A. So mole fraction of C is also 0.5. Okay? So now we can plug this into our equation and solve. I'm just trying to write up here to save space, but if you need to rewrite it, you go for it. And when you add that all together, I got that the total pressure is 319 torr. Okay, so as you're done writing this down, the question did ask us, is this an ideal solution? Well, it told us at 35 degrees Celsius, it's supposed to be a vapor pressure of 260. Is this 260? No. So since our observed pressure is not what it's supposed to be, then it's a non-ideal solution. Okay? So that is it for 310.